Hey, good evening, class. Welcome back, everyone. I'm going to give it a few more minutes to permit more participants to log in, and then we'll jump into it tonight. Hey, Andrew, I see your question about the last lecture. Yeah, I got it posted last night. I apologize about that. The YouTube stopped at 95% when I uploaded it and it never kicked in for some reason. Can you jump to the Moodle page right now and just verify that you can access it? Go there and take a look myself. So let's see here. That was the single supply op amp. Let's scroll back up here. Here we go. So it should be this one right here.
Yeah, because you're applying the input to the positive pin.
That's good. So load it up there. Hopefully that's working for you as well. Yeah, again, I apologize about that. I'm going to make a better effort to make sure that these videos get posted in a timely manner for you to access. We'll go over the MOSFET stuff tonight because that's going to be the next lab that we jump into. But if there's any remaining questions, like I had two students reach out to me about the potentiometer. We can circle back around to that at the end of the lecture, if well, at least the information, introductory information to begin a lab and discuss it. All right. When is lab 4 due? Good question. So let me pull up my calendar here. I'll say ideally I'd like everybody to have it in by the 12th, so next week at by the start of class. But as far as from a points perspective, Mario, for some reason, if it lingers on a little bit, if you're having some difficulties at the lab, I've got it open-ended on all the labs to where anything that trickles in past that point between then and the end of the semester, I'll grade it then, you'll still get full credit for it. I'll just emphasize again, I think it's to your benefit to the quicker you get it done, the quicker you get to put it in your rearview mirror and just move on to the next step. All right, let's go to tonight. So tonight we're going to kick off lab 5, the MOSFETs characteristics lab. It's from a circuit perspective, it's pretty simple, right? You just got 2 power supplies, a resistor, and your MOSFET. One thing I need to do is to call out, I don't think the CD 4000N MOSFET transistor is in your analog discovery toolkits. So I will research that kit and find a substitute component for you to use in there. But for this week, for the hand calculation and simulation purposes, it's perfectly acceptable just to assume that you're going to be working with this component. So you have a couple of preliminary calculations that you need to do. The beginning stuff is more associated with understanding the region of operation for a MOSFET. Hopefully, It's been explained to you what the threshold voltage is and why you need to overcome that. Stick with the default value of, for simulation purposes, for 4.7K ohms for RD. When it comes to the lab part of it, might specify a slightly different value depending on what's available in the lab kit. Let's see here. Yeah, these are all the hand calculations. They're just giving you some parameters and asking you to, get some data from that. Then for the SPICE simulations, you're going to do a couple different plots. You're going to do one sweep where you're keeping VDD constant, then sweeping VGS. Then you're going to do another one where you keep VGS constant and you sweep VDD. You're not using, I'm sorry, I take that back. You are using PSpice, so you're going to be able to do some of these mathematical expressions here. It's just a means to manipulate the plots to get the information that you need in a visual format to decipher like what region the device is in. But prior to jumping into that, the most common part of this lab that students struggle with, at least in the simulation part, is this part right here. The Appendix 12 and putting the model values into the MOSFET. We discussed that momentarily the first week or two when we went over PSpice, but just to make sure that it's crystal clear on what you need to do, I'm just going to walk you through it again one more time, just so, for the purpose of it to be in the recording in case everyone needs to come back to it. So I've already gone ahead here and built up the schematic itself. Again, it's pretty simple. You got your two power supplies. You got your resistor. For the MOSFET, I will show you this. I just went to place PSpice component discrete, then NPN. So this is how I got the symbol for the MOSFET. I'm sorry, no, not NPN. That's BJT. NMOS. Been a long day. So make sure you select that. Go to PSpice component, discrete, NMOS. You click on that. I'll just show you. I'll drop another one off to the side. And this is this M break in as the generic component that you get. I'm going to go ahead and delete this one since I already have one. And this is what you're working with. So going back to the lab itself, it tells you to assign the model according to instructions Appendix 12.1. All right, so what's Appendix 12.1, you might be asking? You gotta go back to the Moodle page, scroll down to the bottom where all the appendices at, and you're gonna go to SPICE models and schematic entry. I think I've already got it pulled up here, so Appendix 12. And we're using the CD 4007 MOS transistor array, again, just for the simulation purposes and the hand calculations. And here's what you see if you were using this package. You got your package identifier here. It's a 14-pin dual inline package, so 7 pins on each side. Then what you see is you have 3 NMOSs and 3 PMOSs. Your PMOSs are right here, the ones with VDD going to the body. Then you got your NMOSs, which had the VSS going to the body. If you had this package, you would be selecting, let's see here. Let me make sure I got the right one. You'd want to pick one of the devices like this one right here, 3, 4, and 5, where the body bias is isolated, unlike this one over here, which is 6, 7, and 8, where the body is tied to the source. And you'll understand why later in the lab, but hopefully in lecture, you learned about the threshold voltage being 2 components, right? There's a nominal component, which is bias independent. Then there is a bias dependent component of threshold voltage. And the bias dependent has to do with the bulk to source voltage. Well, on this device over here, the bulk to source voltage is always 0, right? Because they're tied together, they're at the same potential. But this one here, you can change the bulk to source voltage depending on VSS. Well, this is where it's a little confusing. VSS, this part, is actually pin 7. So that'd be like, it's saying that all these VSSs here and here are tied to pin 7. So you could manipulate the threshold voltage by changing the body voltage, and that's something you'll see in this lab. You can either make it a larger threshold voltage, which might be advantageous for an application where you want to have a really low leakage current, or maybe you need a device that switches really fast, right? So you lower the threshold voltage. All right, anyways, so going back to this, here's your model, and what you're going to want to do for simulation purposes is come in here and select this. The reason I'm only selecting the first part is because we're only doing the NMOS. You're not simulating the PMOS. So just the NMOS. Come in here, go copy. We go back to our schematic. I'm going to left click on the device to highlight it. I'm going to right click on it, and I'm going to go to edit PSpice model. So not edit part, but edit PSpice model. So you're going to click on that. You know, as always with PSpice, nothing appears. You got to come down the toolbar. You're going to click on this model tab down here. You can leave it on the first option. The option doesn't matter. Hit OK. And I'm just going to increase this here a little bit. So right now, this is just the default model setting. It's just dot model mbrake n. So what we're going to do is we're going to come in here, delete that. We're going to do a Control V and paste the model for the NMOS. So one thing you might be asking before I go any further is, well, what is this model? What does it represent? Anytime a foundry produces a component or manufactures a component, they're going to characterize it. And by characterize it, I mean pull, like, you know, electrically stimulate the device and pull curves off of it. And these parameters go into a model. And that model, you can think of it as just a really big mathematical equation that's a curve fitting equation. So like if it has a specific gate and drain voltage bias with respect to the source, like maybe this model would calculate what the current is going through the different nodes. So in order, if you have any background with curve fitting, it's based on a bunch of parameters. Well, that's what all these parameters are in here for, is for that model to make the curves match what is physically being produced at the manufacturing site. All right, so we got everything dropped in here and saved. We're gonna go to File, Save. Now I'm just gonna minimize it. I like to keep it open on the bottom in case you gotta go back there and change anything. But hopefully what you see now is, notice the name of the component is changed, that MCD 4007N. There you go. So now at this point, you can go through and run all your simulations. Let's see here. One thing I did just notice though is that this symbol in particular has the body and source tied together. So we're probably going to have to use a different PSpice component. So let's see if we can find something else here. Let's see, I'm going to do a search. Let's see here. I wonder if I can find it in here. I got the mbrake. There should be a 4-terminal one. Let's try this. I'm going to try MOSFET in the search. No, that's not what I'm looking for. mbrake. There we go. This is the one you want to use right here. So I typed mbrake in search, and you want to use mbrake 4. So I'm going to double click that. Let's see if we get this come. Here we go. Okay, much better. All right. So here's why I'm selecting this one. See how the body and source are isolated? They're their own terminals. They're not tied together like this. So this is the component that you want to use. So I'm going to delete this component. I'm going to drop this component in its place like such. I'm going to connect the rest of these wires up. And the last thing I'm going to do is, well, two things. I'm going to add one more voltage source for the body right now. And we'll just leave this one at 0 volts. And then we're going to come back in here, go edit piece-by-piece model. Oh, we've already got one open. It doesn't like that. So I'm going to close this out. Go to edit piece-by-piece model. Open that back up. Hit OK. Now let's delete this and copy the parameters back in. Hold on, it crashed. All right. Yeah, this is one of the difficulties with the piece-by-piece model editor is that it gets a little finicky. Let me try this real quick. Let's go to edit piece-by-piece model. Yeah, it doesn't like it. Okay, so I'm going to save this. I'm just going to close my project for right now. Go to File, close, File, close. And I'm going to come back in here. I'll open the MOSFET. Would I save the project back open again? Let's see here. Go back to the schematic. And we'll try this again and see if it works. Edit piece-by-piece model. No. Okay, so I'm going to have to close the whole thing out, unfortunately. So I'm going to come back in here. I guess this is a good way. This is a common thing you encounter, unfortunately, with this tool with the model editor. So I'm going to come back here, just relaunch everything. Okay. And my project should be saved. So I could just open it back up at this point. So I got my MOSFET lab, pop that back open. All right, hopefully this works. So select the component, edit piece-by-piece model, and perfect, pop back open on the bottom, hit OK. Hopefully it doesn't crash on me this time. I'm gonna delete that. Okay. Maybe it's what I'm trying to paste into it is I gotta go back and, yeah. All right, I apologize. Hold on, just bear with me real quick. Let's see here. Okay, lab's open back up. I'm going to go back to the class website here. This might be part of the problem. I'm going to Control C, copy that again, come back over here. And hopefully this works this time. Maybe we just need to refresh the copy buffer. All right, the model's open, hit OK. And come in here, delete that, Control V, paste it, perfect. Okay, yeah, there was something I must have saved along the way I didn't like. Hit save, I'll close this out this time, come up here, hit save. Okay, so now we got our schematic set up here, and I'll just show you a few things real quick. So PSpice, new simulation profile, MOSFET. Let's see here, that's good. We're going to do a DC sweep. We'll do the source first, so that's source V1. V1 will go from 0 to 5 volts, and it's like 100 millivolts, 0.1. Okay. Let's put a voltage probe here on the drain. And we'll do one here on the source. And go ahead and run it. Just make sure everything works, right? Get our plot to pop up. And here we go. So voltage is going up on your gate to source voltage. Now this is your drain to source voltage, right? So that's the voltage between your drain and your source. Your source is at ground, so it's below the resistor. So hopefully conceptually this makes sense, right? So when the gate voltage is 0, you're below the threshold voltage. The MOSFET is not conducting any current because no channel has been formed yet. So your VDD voltage, which is set to 5 volts, is present across the drain, right? So that's your drain to source. As you increase your gate to source voltage, eventually you get that inversion layer in the channel to form, right? You start accumulating a really big positive voltage on the gate, you get a bunch of electrons forming in the channel, and you get that channel formed between the drain and the source. And now you have a voltage controlled current switch essentially, to where as the gate source voltage gets bigger, more current flows through the device. As more current flows through the device, you get a larger voltage drop across that drain resistor, right? So as you have more voltage dropped across the drain resistor, I'll go back to the schematic real quick. This guy, RD right here, as more voltage gets dropped across here, there's less voltage from the drain to the source. Then it pulls it all the way down, the lower value down here. Let's see. So I'll leave it at that at this point. The remainder of the steps in the lab are just performing different sweeps. So we swept V1. There's another one where you set a fixed voltage on the gate to source voltage and you sweep VDD and you get some different values. But the key thing I wanted to point out was just how to get the parameters under the model card so you can perform the simulation. Let me go back to the lab. So let's see. Tonight's night 1 of the MOSFET lab. So this is a 2-week lab. I will follow up via email with advice on what component to use. But essentially what I expect between this week and next Thursday is for you to get through the preliminary calculations, so steps 1 through 3, and perform SPICE simulations 4 through 7. Then the lab experiment, we'll jump into that next week. That's just appears to be 4 steps, 8 through 11. Then I'll comment next week on like which of these conclusion items you should address in your report submission. I will say this, so any questions that have you do a comparative analysis between your hand calculations and simulated values and the actual circuit you build up, you go ahead and compare your hand calculations to your simulation values because you're using the 4007 MOSFET for those. But don't worry about the measurement values because that's going to be a different component. It's not going to be this CD 4007 more than likely. Okay, at that point, I'm going to turn it back over to you. See if there's any questions at this point, and see how everyone's doing. So if you have any potentiometer example. Okay, all right, Andrew. Okay, by example, do you mean in the simulation environment? You know what? You can't do it in the simulation environment. That's just going to be on your board. The best you can do, so let me address that. I'm going to go back to the previous lab since a couple of questions came up on that. That was not a requirement. Let's see here. Coming back to the previous lab. So here's your potentiometer right here, right? 3-terminal device. For the simulation, you were to use, let's see here. So for step 5, you recognize that the potentiometer is used to create a variable DC voltage, a VREF. So in SPICE, do not use a potentiometer, but simply connect VREF to a DC voltage. And again, disregard these values. We're using everything split in half because you're 82 kits. We're only capable of going up to 5 volts. So you want to use a VREF of 2.5. So what you would do for simulation purposes for this schematic right here, you would disregard the potentiometer right here, and you just connect a DC source from VREF. So from this, the bottom of this 22K ohm resistor to ground, and you'd set it to 2.5 volts. Does that help? Okay, then the last thing I'll comment on, maybe you've already figured this out, but once you go to build up your circuit, there are some potentiometers available for you in your kit. They're a 3-terminal device. I think they included even the little screwdriver too to adjust them. Here's what I recommend if you haven't done so already. The 2 outer terminals are your rail terminals, and they're interchangeable. Like, it doesn't matter which one. You could hook one up to VCC and the other one up to ground, or vice versa, okay? The middle terminal is your tap point for your VREF. So here's what I recommend doing. Prior to hooking your whole circuit up to the potentiometer, I would just hook VCC and ground up to it and adjust the screw on it until you get VREF equal to 2.5 volts, and then connect the rest of your circuit up to it. So hopefully that helps. Yeah, Mario, good point. Let me scroll back down here to the bottom. Okay, for step 1, I just want you to, honestly, you can take a screenshot of that, or just even in the notes, write down what you observed for the clipping levels for V out as a function of VN. If you want to go one step further, you could put them in a table in Excel and plot them. Let's see, number 2, restate your data from step 10. Restate your data from step 10. Let's go back to step 10 real quick. The DC bias via, so restate your data from September regarding the DC bias voltage at the input and the DC bias. What is the relationship? Hopefully, I'll go back to it. This is a little bit of circuit knowledge here, but hopefully from a DC perspective, what you recognize here, and I believe this is on the initial video, is that this is just simply a buffer when it comes to DC. So V out should equal VN, with the exception of an offset voltage. There'll probably be a difference there because of that. Let's see, so that's 1 and 2. Yeah, definitely show your calculations for the 2 poles. Yeah, item number 4. Yeah, for step 13, yeah, so I'd recommend to get straight to it. Answer all items 1 through 5. Hopefully what you realize on item number 5 is that your DC bias input would have to be so small. Again, going back to the top, if you got rid of this capacitor and just connected this resistor to ground, your DC and AC gain become the same. And your DC and AC gain is probably somewhere between 30 and 45, right? That's what the spec was. So in order to get V out to be 2.5, you gotta do 2.5 divided by somewhere between 30 and 45. That's a really small number. If you look at the data sheet for this component, you're gonna see that the input common mode range, you probably gotta have like 1.5 to 2 volts on the input to get it to work. So in short, the circuit won't work just because of bias conditions. But yeah, so address conclusion items 1 through 5. Good deal. So I will say this: after the MOSFET lab, we had the BJT lab. It's going to be a little bit more complex than the MOSFET lab, but I believe we'll have an extra week on that one. So we'll get everything covered. If there's enough time at the end, I'll go through a design example with the BJT. But as far as schedule-wise, you guys are definitely on schedule and everything's coming together. Hopefully everything's going good for you in lecture, and that you're getting what you want out of the class. Any more questions? All right. Well, if you got no more questions, go ahead and jump off. Over the course of the next week, get everything done as far as the preliminary calculations and simulation stuff for the MOSFET lab. And at your convenience, as you wrap up the single supply op amp lab, start submitting your reports through the Moodle site. And for office hours next week, in case any questions pop up, feel free to shoot me an email and I'll schedule time accordingly to sync up with your schedule and get those questions answered if you need any help outside the normal lab time. All right, well, I'll hang out for a little bit longer if anyone has some additional questions. If not, have a great evening.